Hi, welcome back. Hopefully, you have reviewed what we have learned previously in the last homework. And today, we're going to continue to show how useful it is for the theorem of the locally bounded. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, a positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a. Okay, it's called a around at the point x0. So it means if we choose the neighborhood of x0, right, defined by the formula here, Okay, this is like x0 minus delta. This is like x0 plus delta. So in this region, now we have the f(x) in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct, because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Locally bounded. Okay, so how can we prove this? All right, let's continue. So we can make it sound more general. So for any interval, as long as, sorry, let's change color. Okay. So for any interval, I will use I standing for interval. As long as it is well closed, it means the function is defined on its two endpoints. We can say that, well, if the function is continuous. Okay, the function is continuous. And then the function f(x) must be bounded within the interval I, which is between a and b included. Okay, so that's very easy. You can also try or imagine out of functions you have learned so far. As long as the functions are defined within the closed interval you choose arbitrarily, you can say that f(x) is locally bounded within that closed interval. So we have no problem with this. And we say that, well, for the interval which is open, now we have two cases. Well, in some cases, we cannot say the function is locally bounded. But for some other situation, such as the second example we have in the last slide, now we can say that the function is locally bounded. So for this, we will have to use some skills to test it out. So remember, this is very important. Hopefully you can write it down repeatedly, remember it, which is going to be very useful for your future classes or careers. Okay, so in this open interval, we have test on 3 points. The first point is, okay, so according to our locally bounded theory, we can say that if the function has a limit when it is approaching to a certain point, now we can say that this function value is locally bounded, right? So we have to say yes for the point A, so when x is approaching to A. And this time, because A is on the left side of the interval, so we're approaching it from the right. So we have to use the plus sign here to indicate we're approaching A from the right. Okay, so we can say that the function, we can test it out to see if it has a limit or not. Well, the sign here, remember, it means exist, right? We just want to simplify the words here. So it means if we have a limit here, for example, we have limit A, like this symbol we used in the theorem of locally bounded. So if there exists one limit for this function when it is approaching from the right side of point A, now we can say that, well, it is past the first checkpoint. Okay? So similarly, we can do the similar thing on the checkpoint B. So when x is approaching B, and then we can see that because B is on the right side of this interval, so we have to approach B from the left side. So that we use minus here to indicate this direction. So if there's also exists one limit of a function, if x is approaching to B from the left, now it passed second checkpoint. Okay, third one is, alright, so although we say if we have this closed interval, for example, we can say that universally, this is very simple. If a function is defined totally within a closed interval with the endpoints included, there's no doubt this function is bounded. Well, in our case, we change it to open interval here. I use another color. Okay, so we change it to, the open, yeah, case here. Although we cannot say right away that the function is, totally bounded. It may have definite value on the endpoints positions, right? However, now we can say that if, similar to the definition of the limits, so we can imagine if we have a delta 1, which is positive, and then we have a delta 2, which is also positive, we can say if we just move the boundary on the left a little bit to the right, or to say we move the right boundary a little bit to the left, we can say A minus delta 1 and B minus delta 2. So we have something like this shown here. Okay, and the delta 1 can be as small as possible, right? It can be 0.00001, right? It just means we will not take the point right at endpoints like A or B, but we'll just make the boundary a little bit, move it a little bit to the left or to the right, so that we can say within this new interval, everything will be, bounded, because this is a closed interval. This new one is closed. So we can see we are sure, within this, the function is bounded. And just like the definition, or from the for the function limits or series limits, we have seen the delta many times before, because it can be as small as possible. So actually, you can say fx is continuous within A to B, excluded. So see, if it is continuous within this open interval, because we can draw such imaginary new closed interval within the open interval. Now we can take advantage of the first condition. Well, as long as fx is continuous, we can say, yes, fx is bounded within this closed interval. So we can say that, yes, for the checkpoint number 3, fx is continuous. We can say within this open interval A to B, now we can say that, yeah, it has the third checkpoint. Yeah, so for such problem we shown here, we want to check these key points out one by one. So if, like for example, C has all of these 3 checkpoints, now we can say that within that certain interval, the function fx is locally bounded, right? All right. So welcome back to this problem. So now let's analyze it. Now we understand, although fx looks maybe very complex, however, it is still what we call the elementary functions. Okay, elementary functions. What is that? Don't be scared. They are nothing but the basic functions we have learned so far, such as the absolute value of x, the sine x minus 2, the trigonometry functions, the first order, second order functions here like x minus 2 squared. Yes. Basically, it means all of the math courses talking about functions you learned before the university are called elementary functions. And that is why we call, the mathematics in college advanced mathematics. Because no matter, how many simple, or to say the elementary functions you put here, you wrap them together, as long as the operation are limited, such as you plus the function, minus the function, times the function, divided by a certain function, as long as, the number of operations are limited, you can make it to 1 minute. We still call it the new function you made, fx, elementary function. Alright, so, be confident. We're gonna talk about it But we understand that from your education from high school, you have to find out, well, if this function is defined in every certain point. So we found out that basically we have x on the denominator, so it means x can never be 0, or to say it can never be 1 because we have x minus 1 here, or to say x cannot be 2. It seems like we have 3 points which are not defined for this function f(x). However, we understand that for each elementary function, they are all continuous. You can try this. You can try maybe the sine x minus 2 here. You can draw the graph, or you can Google online or use your computer to draw the graph. You will find out that as long as the function is defined within a certain interval, it will be continuous. Okay, so that's why we see the choices here that are all open intervals, because for certain points the function is not defined. And also from what we discussed previously, if the f(x) we understand is an elementary function, and an elementary function is always continuous within their defined interval. So if he will give you just like 3 to 4 included, it will make this question too simple, because f(x), which is continuous, right, is always bounded within a defined interval, the closed interval. Yeah. So that's why, we have to look for something more complex here. You think about it. Alright, so we talked about that we have to verify those 3 key points one by one. So why don't we start from the first one? The first one is, we understand, for example, for the choice A, we have -1 to 0 excluded. So if we want to test out if the function f(x) is bounded within the such open interval, we have to first find out if we have a limit on the point -1, and then we find out if we have a limit for the function f(x) on a point 0, although it is not defined out. But what about the limit? Does the limit exist? Okay, so let's try the first one. The first one is, okay, limit when x approaches to -1 from the right. So this time, let's look at this. So if we choose -1 here, now we're gonna have, I will just write this down again to make it maybe look more clear. Okay, so just some basic limit calculations. So it means, so for example, so when x is approaching to -1 from the right, so we can say, so this time absolute value of x is almost 1, and then we will say the sine -3, because x is almost -1. -1 minus 2 give us -3, so -3. Don't be scared, you don't need a calculator here because it doesn't matter. You don't have to find out the specific value. And also on the denominator position, we have x as -1 is almost at -1, and then we have x -1 will give us -2 here, and then we're going to have x -2 give us -3, and -3 squared will give us positive 9. It's okay. I would just leave it like this. So you don't have to calculate it, because from your knowledge, you understand, this, of course, are just numbers. And this one is also a finite number. And also, it is not only finite, but also very small. It can only be within from -1 to positive 1. So we can say that, yes, of course, this limit exists. Yeah, so we can say, yes, this limit exists, and from our locally bounded theorem of limit, now we say that f(x) in the local area of this point -1 is also bounded. Okay, so similarly, let's try the right endpoint. So when x is approaching to 0 from the left, so now we can say, okay, so this one is, okay. Okay, the reason I repeat writing this is, so let's look at this. That's why I always mention direction when the x is approaching to a certain point. It is approaching the 0 from the left. But but after we can say, for example, x equals to minus 0.01. Okay, so it's very small, it's very close to 0, and also we can say that it's approaching to 0 from the left. Yes, so this time, now we can get rid of the absolute value here, so we can say it is minus x because it is still a negative number, so that's why we have to put a negative the minus sign here. So now we can see, yes, x and x can be cancelled out. Okay, so now we can say for 0, what is left is don't forget a minus sign on the left, and 0 minus 2 will give us minus 2 here, and on the denominator part we have 0.1 will give us minus 1, and then times 0 minus 2 will give us minus 2, and minus 2 squared will give us positive 4. You don't have to calculate out, you can just leave it like this. And still, we understand sine, no matter what inside of the sine function, it's just a number between minus 1 to positive 1. And also, on the denominator, we also have the finite numbers here. So, we understand as a whole, the limit exists, right? So now we can say that according to the locally bounded theory, we just learned in the last lecture, similar to what we have here. Because we have the function limit exists at the point 0. So we can say that within the local area of 0, the function fx is locally bounded. And then we don't have to do, well, this is key point 1, key point 2, and key point 3. And we understand that fx is continuous. It's continuous because it's an elementary function composed by different small elementary functions. So it's definitely continuous within its defined interval. We understand that from minus 1 to 0 is definitely defined, right? Although x can never be minus 1 or to say or 0. However, within this, the fx are defined, and also we understand fx is continuous, so that we can say yes, fx is bounded, within such open interval, and altogether, since we have checked, the two endpoints one by one, now we can conclude that fx is bounded. Now within. Alright, that's all for today's lecture, and in the next one we're going to learn the last property of limit. So today's homework is I want you to review the property number 1, uniqueness, and also the property we have just talked about, the locally bounded theorem. Alright, so in the next lecture we're going to talk about the last one. You can guess what that will be. See you next time.